Hi guys, let's derive expression for capacitance of a parallel plate capacitor with a dielectric. So we know that dielectrics are the very helpful to increase the capacitance of a capacitor. I need to derive a mathematical expression. So before that, I would like to recall what we learned from a capacitor. Let's consider this a ordinary capacitor. It's a without dielectric. So here the yellow shaded region is an air medium or vacuum. It's an ordinary capacitor, no dielectric at all. So to this capacitor, suppose if I would like to write the capacitance expressions, capacitance of a capacitor, I would like to take C suffix naught, C naught equal to epsilon naught A upon D. So here A is the area of the plate and D is the distance between the two plates. And I would like to write the electric field between the electric field between the capacitor plates. E suffix naught equal to sigma by epsilon naught. Here the sigma is nothing but the surface charge density. If I take surface charge density as capital Q A upon epsilon naught. So here Q is surface charge density. And we know one more relation, that is electric field and potential. To find the potential between the capacitor plates, potential V equal to electric field times the distance. So where you want to find the electric field. So these three are the earlier knowledge we know from the capacitance of a capacitor. So here epsilon naught equal to permittivity, it means it's a medium just like air or the vacuum, not any another material medium or not any another dielectric medium. So with the help of this knowledge, so I would like to extend the expression for capacitance of a capacitor with dielectric. Suppose here you can observe a dielectric is kept inside a dielectric medium. So the thickness of the dielectric equal to small t. It is kept inside the dielectric medium. Inside the between the plates of a capacitor. Now what happens? First thing here, if you can closely observe, the charges gets polarized and positive charge and negative charge. They will polarize. So because of the polarizations, we can notice an electric field due to polarization. So that is the amount of the electric field due to polarization which is inside the capacitor plates, inside the dielectric medium. And if you can take E naught is the external electric field and E suffix P is the electric field due to polarization, we can notice there is a residue electric field. So if you can notice it here, this is the residue electric field within the dielectric medium. Now I would like to write the expression for electric field first due to the polarization and the electric field which is the leftover electric field within the dielectric medium. Suppose I would like to write the electric field, the induced electric field, E suffix P is given by, so electric field between the two plates, that is also goes to surface charge density sigma suffix P by epsilon naught. So here sigma suffix P is the surface charge density due to polarization. So that is the expression for the electric field inside the dielectric medium. Now if I want to write the expression for the net electric field, inside the dielectric, the net electric field inside the dielectric E equal to E naught minus EP. So here E naught is the applied external electric field because of the external two plates. So and the E suffix P is due to the electric field due to polarization. Electric field due to polarization. And E naught equal to applied electric field. Now if you can recall the relation between applied electric field to the residue electric field. So here E also we called as residue electric field or net. Residue is nothing but net only. So which is the leftover. If you can recall the relation between kappa is nothing but E naught upon E naught minus EP. So from this expression, if we can write E naught minus EP, which is equal to E naught upon kappa. So this is the expression for E naught minus E suffix P. So if we can write that small correction, so that is the E suffix P, electric field due to polarization. Now, if you can write the potential expression, the potential, the electric potential between the plates, the electric potential between the plates. So we know the electric potential and electric field relation. So from this expression, if we can take, so it is without the electric field, without the dielectric medium, the potential V equal to E times D. Now after keeping the dielectric, here the two electric fields are there. The electric field due to the external because of this positive plates, and the electric field due to the inside the dielectric medium. Now if you can write that expression, the total potential V equal to, here the E naught equal to electric field due to the outside, and I can write the expression D minus T. So here how it is a D minus T? Here the D is the distance between the two plates, and T is the thickness of the dielectric medium. So to get the leftover space, so the remaining part without the dielectric is nothing but D minus T. So that's why we got that D minus T there. And plus, since potential is a scalar, we can add it. Now the electric field E due to the dielectric medium, so here the E is the electric field due to dielectric medium, and T will be the thickness of the dielectric medium. So here the T will becomes thickness of the dielectric medium. So here if you can observe carefully, two electric field expressions are there. So this E naught is the electric field due to parallel plate capacitor. Electric field due to parallel plate capacitor without dielectric. And here E is the electric field inside dielectric, and the d minus t is the leftover space after keeping the dielectric. D minus t equal to remaining space. You can take that. Remaining space after keeping dielectric. So d minus t equal to remaining space after keeping dielectric, and here the t equal to thickness of the dielectric. Now that formula you always match with the relation between electric field and potential. The relation between electric field and the potential V equal to ED. And here the potential is a scalar term, so we can add it up, that scalar term. Now in the place of E, so if you can substitute that values, so if V equal to, so I can write that same expression at the down. So V equal to E naught of d minus t plus E times t. So from the above expression, so E naught is the external, t plus the E means at here the residual electric field. So here the E terms which I used at here the residual electric field. So if you can write that as E equal to, this is the term, E equal to E naught minus E suffix p. So in the place of E, we can directly substitute the value of E naught upon kappa. Because if you can write the relation, kappa equal to E naught upon E naught minus EP, which is also equal to E naught upon by E. So here E means which is the leftover electric field, only we are calling E naught minus EP. Now the leftover term here, the T is the thickness of the dielectric slab. Now if we can simplify this, here the E naught is a common factor, so D minus T plus T upon K. So this is the final expression if you can write it. So let me write the T properly, and if you can substitute the E naught value from the very first expression, what is the electric field due to the two parallel plate capacitor. So the electric field between the parallel plate capacitor, the E naught equal to Q by A times epsilon naught. So that value if you can substitute at here, so E naught equal to capital Q upon A epsilon naught times D minus T plus T upon K. So this is the potential expression. But we need to calculate the capacitance. Since capacitance C, if I call C is the capacitance after keeping the dielectric, capacitance C equal to, what the expression you can write, Q upon V, total charge by total potential. So here the total charge Q, the potential expressions I can take from it here. If you can substitute in this value, so it equal to Q upon A epsilon naught times D minus T plus T upon K. Now this Q gets cancelled, and if you can do the reciprocal, the capacitance of a capacitor with dielectric, C equal to epsilon naught A upon D minus T plus T by kappa. Sorry, that is supposed to kappa. dielectric constant kappa. So this is the final expression for capacitance of a capacitor with dielectric medium. Now if I take a special case, the special case is if D equal to T, it means we will fill the entire space with dielectric. So in this case, if you fill the entire space with the dielectric, this everywhere with the same dielectric material, if you can fill it. Now we would like to find out that what is the final expression if we can fill the entire space with the dielectric medium. So what could be the expression for the capacitance? So in that case, if you can write if the filled with the entire the space, therefore from this expression I can change that D equal to T. That T itself becomes as an occupied with the total capacitance. So this expression will be changes if D equal to T, in the denominator epsilon naught A upon, so I can replace that D minus D plus D by K, sorry, kappa. So these two terms gets cancelled, therefore capacitance of a capacitor C equal to epsilon naught upon times kappa by D. So this is the capacitance after capacitance of a capacitor with the dielectric field. With the dielectric. Suppose if I write an expressions, capacitance of a capacitor without dielectric. So that we have written, I have taken that C naught equal to epsilon naught A upon D. So that is the capacitance of a capacitor without dielectric. So in the place of epsilon naught A, if you can replace that term in the above expression, I can replace this there. Therefore capacitance of a capacitor, the capacitance with the dielectric C equal to C naught times kappa. So this expression tells about if you can keep a dielectric inside a capacitor, so the capacitance of a capacitor increases. How much time it increases? It increases kappa times. So here the kappa is nothing but the dielectric constant. So here one more important point. So to increase the capacitance of a capacitor, we need to choose certain dielectric constant material which is having more. So if the dielectric values increases, let's observe from it here. So if you can closely observe on the right side, I am having an option which I can increase or decrease the dielectric constant. So if you can closely observe here the dielectric constant on the mouse cursor, so it's the dielectric constant is increased as 2.35, sorry 2.33. If you can observe on the capacitance value, it is 2.06. Suppose if you can take the dielectric constant value as a 5, if you can see the capacitance of a capacitor value increased to as 4.43 times 10 power minus 13. It means the capacitance of a capacitor is also depends on the dielectric medium. So the dielectric medium having different dielectric constants. So we will find it out which is the better material which is having higher dielectric constant value. So that value will be replaced to increase the capacitance of a capacitor.